Have you ever wondered what would happen if GPS just stopped working? What if you could still navigate with absolute precision even if every single satellite went dark? Well, today we're going to dive into a technology that promises exactly that. It's called quantum navigation.
I mean, really think about it for a second. Your phone, your car, the plane you might be flying in, global shipping, even the stock market. Pretty much our entire modern world leans on this network of satellites orbiting thousands of miles above our heads. So what happens when that signal just vanishes? And this isn't some far-off hypothetical. Nope, it's already happening. That Spanish military plane, which was actually carrying the country's defense minister, landed safely, thank goodness. But here's the thing. It was just one of thousands of flights that have been hit by GPS interference. This incident really shines a spotlight on a massive weak spot in a system we all completely take for granted.
Okay, so let's really get into this vulnerability, because the threats to our GPS systems are getting more and more common and, frankly, a lot more sophisticated.
You've basically got two main flavors of attack. First up is jamming. Think of this as the brute force method. It's like someone screaming so loud in a room that you can't hear the person whispering to you from across the table. It just drowns out the weak satellite signal with a blast of radio noise. Then there's spoofing, which is way more sneaky. This is where you feed a GPS receiver false information, tricking a plane or a ship into thinking it's somewhere it's not. Both are really serious threats.
So, with this growing threat, you'd hope there's a solution on the horizon, right? Well, there is. A totally new approach is emerging from the world of advanced physics, and it could be a powerful backup.
And this is where quantum navigation enters the picture. You see, instead of looking up to space for a signal, this technology looks inward. It taps into the super weird, but also super predictable, behavior of atoms at the quantum level to create these incredibly precise sensors that can figure out their own position all by themselves. And this right here is the fundamental difference. GPS is always looking outside for help. It's completely dependent on those external signals, which creates a huge single point of failure. But quantum navigation, it's self-contained. It doesn't need to listen to anyone, which makes it totally immune to jamming and spoofing. So how on earth does this stuff actually work? Let's unpack the first of two big ideas here. And this one is all about having a perfect sense of your own movement, every single second. It's a concept called inertial navigation. The idea behind it is actually pretty straightforward. If you know exactly where you started and you can perfectly track every single turn, every change in speed, and every second that goes by, you'll always know where you are. The problem is, even the tiniest little error in your measurements starts to add up, and they add up fast. A standard system could be off by 20 kilometers in just a couple of days. That's fine for a submarine in the middle of the ocean, maybe, but it's totally useless for a pilot trying to find a runway. And that's where the quantum magic comes in. It's a technique called atom interferometry. So, picture this. First, a laser zaps a cloud of super chilled atoms, splitting them and sending them down two different paths. As the plane or ship moves, turns, or accelerates, those paths change just a tiny bit. Then another laser brings them back together. Because their journeys were slightly different, they're now a little out of sync. By measuring that microscopic difference, the sensor can calculate its own motion with just mind-boggling precision, fixing that drift problem we were just talking about. Now, to pull all of this off, you need another superpower: perfect timekeeping. And that's where companies like Inflection come in. They've built these incredible, portable atomic clocks, like this one, the ticker. It uses lasers to get rubidium atoms all excited, and when they calm down, they release light at an insanely consistent rate. It's like a perfect pendulum, ticking at the atomic level. The kind of accuracy we're talking about here is just staggering. Okay, get this. An atomic clock like the ticker is so precise, it would take 2 million years for it to be off by just one single second. Let that sink in. When you can measure time that perfectly, you can calculate how far you've traveled with amazing accuracy. All right, so that's method one. But there's a whole other way quantum navigation works, and frankly, it's maybe even cooler. This one isn't just about tracking yourself. It's about reading an invisible map that the planet itself provides. So here's a fun fact. The Earth's magnetic field isn't this smooth, perfect thing. It's actually kind of lumpy and bumpy with tiny fluctuations all over the place.
And we've mapped these variations meticulously. So if you have a sensor that's sensitive enough to read these little local differences, you can just compare what you're seeing to the map and boom, you know exactly where you are. It's like the planet has its own built-in, totally unjammable fingerprint map.
So how do you build a sensor that can read that map? Believe it or not, with diamonds, specifically nitrogen vacancy diamonds. These are lab-grown diamonds with a very specific flaw. Think of it as a perfect imperfection. There's a nitrogen atom right next to a spot where a carbon atom should be. This tiny defect creates a quantum state that is ridiculously sensitive to magnetic fields, which makes it the perfect core for a quantum magnetometer.
So these new quantum sensors are a total game changer. Older sensors could just measure the strength of the magnetic field, but these new ones, they can also tell you which direction the field is pointing. And having both of those pieces of information makes finding your exact spot way, way easier. And this isn't just theory. These things are already being tested in real-world flights right now.
Okay, but here's the catch. There's always a catch, right? Taking these incredibly delicate instruments from a quiet, clean, stable lab and sticking them inside a rattling, vibrating, turbulent airplane, well, that's like trying to listen for a pin drop in the middle of a rock concert.
And don't just take my word for it. Listen to this from Michael Bierchuk, the CEO of QC Troll. He says there's usually 100 to 1,000 times more noise than the actual signal they're trying to find. The vibrations, the electronics, the metal body of the vehicle, it all creates this storm of noise that can just completely swamp the tiny quantum signal.
So you see, you can't just build a better box. The real genius here is in the software. Companies like QCTR are developing some seriously powerful algorithms and machine learning that can sift through all that chaos. It's like giving the sensor a perfect pair of noise-canceling headphones, letting it hear that tiny, crucial signal loud and clear.
And does it work? Oh yeah, it works. In recent tests, QCTR's system was able to track a plane's location with up to 94 times more accuracy than a conventional high-end system. That's not just a little bit better. That's a whole new league.
So, does all this mean that GPS is on its way out? Are we just going to throw it all away? Not even close. The future of navigation isn't about replacement. It's all about resilience. It's about teamwork. The key concept here is sensor fusion. Think of it like a superhero team for navigation. The systems of the future won't bet everything on one technology. Instead, they'll intelligently combine data from every source they have. GPS when it's working, quantum sensors, those magnetic field readers, even cell towers. They'll fuse it all together to create one single, super robust and trustworthy picture of where they are.
So why does all this matter? Well, for that submarine deep under the ocean, or that airliner flying through a jamming zone, or even a self-driving car in a city where GPS gets patchy, quantum navigation is a lifeline. It provides a powerful, independent backup that can keep things moving safely when that signal from space goes dark.
And make no mistake, this isn't some far-off sci-fi dream. It's happening now, and it's getting better, fast. As researcher Lofty Masarwe puts it, right now, we're talking about systems that are stable for tens of minutes. But the moment they're stable over 1 week, at that point, it's not just an improvement, it is a complete game changer for how we find our way in the world.